The fundamental theorem of calculus. The mean value theorem of integral. If f is continuous on a closed interval AB, then at some point C in AB, the f average or f, there is a C that would make this happen. F of C is equal to the 1 divided by b minus a times the integral from a to b of f of x dx. Now geometrically, the mean value theorem says that there is the number c in AB such that the rectangle with the height equal to the average value of f of c of the function and base width function and the base width is b minus a have exact same area as the region beneath the graph of f of x from a to b. Okay. So how do we want to prove this? So let's try this. Show that if f is continuous from a to b and that a is not b, and if the integral from a to b of f of x dx equal to 0, then f of x equal to 0 at least once in a and b, okay, in the interval ab. So we know earlier in the previous section, we know that f average, the average of the function, go 1 over b minus a times the integral from a to b of f of x dx. Now we are given that the integral from a to b of f of x dx is equal to 0. This means f average is equal 1 over b minus a times 0 equal to 0. So then by the mean value theorem, f of x must have the value of 0 at some c in the interval AB. Okay. So that's our proof. We use that. Next thing we take a look is the fundamental theorem of calculus, and there are two parts to this. Let's take a look at the first part. If f is continuous on the interval AB, then capital F of x equal to the integral from a to b. The integral from a to x of f of x dt is continuous on the interval AB and differentiable on the open interval AB, and its derivative is f of x. Then f prime of f of x, capital F, is equal to d dx of the integral from a to x of f of x dx equal to f of x. Use the fundamental theorem to find dy dx, given that the integral from a to x of t to the third plus t times dt. Okay. So here we know that dy dx, given dy dx is equal to d dx, the integral from a to x of t to the third plus t times dt. This equal to x to the third plus x. In the next case, we're looking at the integral from 1 to x squared of cosine of t dt. Now, because we have a function here, don't forget we need to use the chain rule. Okay. So dy dx is equal to d dx of the integral from 1 to x squared of cosine of t dt is equal to cosine of x squared times 2x. So here, let's give us our little definition from A, that f prime of x equal to d dx, the integral from a to g of x of f of t dt is equal to f of x times g prime of x. Take a look at the proof of the fundamental theorem. So let's say we are given the function f of x. Then f prime of x is the limit at 8 approaches 0 of f of x plus 8 minus f of x divided by 8. This is equal to the limit at 8 approaches infinity, I factor out 1 over 8 of the integral from a to b, a to x plus 8 of f of t dt minus the integral from a to x of f of t dt. I can rewrite this as the limit at 8 approaches 0 to 1 over 8 times the integral from x to x plus 8 of f of t dt. So here we can see that this value 1 over 8 times the integral of x to the x plus 8 of f of t dt is the average value of the function over the interval x and x plus 8. So therefore, by the mean theorem for the integral, there is some c in x in the interval x to x plus 8 such that, so by the mean theorem, mean value theorem, we will have 1 over 8 of x to the x plus 8 of f of t dt equal f of c for some c that is interval. So for c in the intervals from x to x plus 8. So in part 2 of the fundamental theorem of calculus, if f is continuous over AB and f is any antiderivative of f on the interval AB, then the integral from a to b of f of x dx is the value of the antiderivative at the two endpoints. Okay, see how that actually works. So first we go ahead and take the derivative of each of this individual term. So this is 1/3 x to the third minus x to the second plus 3x, and we want to evaluate this from -1 to 1. So first, what happened at 1? So at 1 we have 1/3 minus 1 plus 3. And we take that and subtract, see what happened at -1. At -1 we have -1/3 minus 1 minus 3. This equal 20 over 3. The next case, antiderivative of secant. So recall, derivative of secant is equal to tangent x secant x. Derivative of tangent equals secant squared of x. So before we take the antiderivative, let's go ahead and expand this function out. So get 0 to pi over 6 of secant squared of x plus 2 tangent x secant x plus tangent squared of x dx. So now recall that secant square theta minus tangent squared of theta is equal 1. Okay. So notice that there's two terms here, secant squared of theta and tangent squared of theta. I'll go ahead and rewrite tangent squared of theta in terms of secant of theta. So this telling me that tangent squared of theta is equal to secant squared of theta minus 1. So I go ahead and rewrite this at 0 to pi over 6 of secant squared of theta plus 2 tangent x secant x plus secant squared of x minus 1 dx. And let's go ahead and simplify this a little more by combining like term. The integral from 0 to pi over 6 of 2 secant squared of x plus 2 tangent x secant x minus 1 dx. Earlier, we recall that the derivative of tangent of x equal to secant squared of x. So then now I can write this first term as tangent of x as 2 tangent of x. Derivative of secant of x equals secant of x times tangent of x. So 2 secant of x minus x. And we evaluate this from 0 to pi over 6. And we should get that equal to 2 times 1 root 3 plus 4 minus pi over 6. The next one, here we have a absolute value function. So we have to split our integral into two parts. So let's take a look at what happened with this function. It looked like this, right? So from negative 4 to 4. So I split this into two parts. The integral from negative 4 to 4 of absolute value of x dx is equal to the integral from negative 4 to 0 of the function negative x dx plus the integral from 0 to 4 of x dx. So this equal to negative 1/2 x squared evaluate from negative 4 to 0 plus 1/2 x squared evaluate from 0 to 4, and that equal 16.